In the last section of the book, I began talking about having a function f of x and approximating it well by polynomials near some fixed x coordinate that we typically call a. So you have a function f of x, you have some x coordinate a, and you want to find a polynomial that approximates that function well when x is near a. Why do this? Because polynomials are easy to calculate. We understand polynomials, and so it's just nice. But as I said last time, in the last section, all we were doing was kind of going with our intuition that, if we make the polynomial have the same derivatives as the function f, at a, that makes the functions, or the graphs of the functions, very close together, so it makes the values of the functions very close together when x is near a. That's our intuition, but this is math, and we want to be able to prove something, and what does close mean? And so we'd like to have some bounds on the error. Typically, we can't calculate exactly the error, because if we could calculate exactly the error, then we wouldn't have any, kind of philosophically, we wouldn't have any error if we know it's this polynomial and the error is exactly this, and there was some easy way to calculate that error, then we'd be able to easily calculate the value of the original function. So you don't expect, we have a theoretical result about how much error there is, but in general what really happens is you just get an upper bound on how much error there is, and you don't really know how good it is unless you trust your calculator and ask it. So in this section we are going to look at what's called the remainder. I already called something the remainder when you had a polynomial. This will be a generalization of that. We're going to look at the error and the remainder and just do a couple of examples to show you what kinds of things you can do with it and how you can actually know that what your calculator's display is showing you is accurate to the number of decimal places that the display shows. So last time I introduced the nth order Taylor polynomial. So you've got a function f of x, and we want some polynomial that approximates f of x well for x near a. And this is what we came up with, that this polynomial has its first n derivatives, so it has the value of the function and its first n derivatives at a equal to this function and its derivatives at a. And it's your hope that that makes the polynomial very close to the function when x is close to a. This, of course, assumes your function is n times differentiable. Otherwise, we wouldn't have that nth derivative there. So, okay, what's our question? Our question is, how close is this to this? So we call their difference something, the remainder. So the nth order Taylor remainder I'm going to write r, I'm going to keep subscripting by f, superscripting by n, put the x, put the a. This is, by definition, the value of the function minus the value of the nth order Taylor polynomial for f centered at a. So this is just our definition of the remainder. So if you put this over here, well, actually I'll write the f of x on the left because it looks more aesthetically pleasing to me that way. This is just saying, oh yes, the f of x is the nth order Taylor polynomial plus the remainder. Okay. So this is the nth order Taylor remainder. The error, usually if the remainder is like negative 0.1, you'd like to say, well, so the Taylor polynomial approximates it to within plus or minus 0.1. So when we talk about error, we usually mean a positive number, and you're within plus or minus that. So since that is the way we typically speak, we actually care about the absolute value of the remainder, so the nth order Taylor error. So this is the error in the approximation, to within plus or minus. The nth order Taylor error is E. And it's just the absolute value of the remainder. And this is what we usually care about, and we'll put an upper bound on. We won't be able to say the error is exactly something, but we'll be able to say the error is less than or equal to something, and that's typically what you want to know. So we're going to have one theorem for this. This is Taylor's theorem. The remainder is what I'm about to say. It's a generalization of the mean value theorem with hypotheses that are a little different from the mean value theorem, but only slightly. So this is Taylor's theorem. Suppose f is n plus 1 times differentiable on an open interval I, containing the point A where we want the approximation to be good, containing A. Then, for all x in I, for all x, actually I should say unequal to A in I, because I'm going to say there exists something between x and A, and not equal to x or a, so there better be, x and a better not be the same. Then for all x in I, there exists C. There exists C between A and X. So this means, i.e., and this is strictly between. So if A is less than X, we mean C is between. If A is less than X, then we mean C is between A and X like this. Or if X is less than A, then you would have C here. Such that the nth remainder in the Taylor, in approximating a function by its nth order Taylor polynomial centered at A, equals, and to tell you how to remember this, it looks just like what would be the nth plus first term in a Taylor polynomial, except where you would normally have the nth plus first derivative of f at A, it's at C instead. So this is the nth plus first derivative of f at C instead of A, but aside from that, it looks like the nth plus first term in the Taylor polynomial. So you have divided by n plus 1 factorial and x minus a to the n plus 1. This is Taylor's theorem. It may be completely non-obvious how you use this, but I want to do two examples, and that should be enough to convince you, ah yes, this does tell us things. So let's look at something that we looked at in the last section, approximating E to the point 1. So we had, as an example, we had a f of x, it's e to the x, and we looked at Taylor polynomials centered at 0, so Maclaurin polynomials. I'm going to use our notation for Taylor series, which for now we're not thinking of as functions, they're just formal expressions to say here's what the nth order Taylor or Maclaurin polynomial looks like no matter what n is. So we just don't bother stopping at some n. We just put some dots. So you can either write, so since we're centering at 0, I don't include the reference to a, and I'll drop it from our remainder and error term as well. So you should think of this as t infinity, write either one of these. And we found last time that this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And what we'd like to look at now is, all right, we looked at e at point 1, and we said, oh, well, you can approximate by the first Taylor polynomial. So that's the first order. So you would just say it's approximately 1.01. Great, because this is the value of T1F at point 1. Right, or we also said that, oh, well, we should get a better approximation if we use T3F at point 1. And we saw that we did, believing our calculator for the moment, but it's a little unsatisfying believing your calculator. For instance, how does your calculator know how far out to go in doing this to make sure you are accurate to within your display's capabilities? If you were paying attention just now, and I always hope you're paying attention, you may have noticed that I just wrote something that's wrong. I was saying that the approximation of e to the point 1 by its first Maclaurin polynomial, or its first order Maclaurin polynomial, would be 1 plus x. X is 0.1. This 0 is here just so you don't miss the decimal place, but it's when you add, of course, you should get 1.1, not 1.01 as I wrote, and which stays on the board for a little while. I use 1.1 later when I need it. Hopefully you would have noticed that had we not corrected this, but I wanted to go ahead and correct it. Yeah, that should have been 1.1, and I'm sure somebody would have raised their hand and said something about that in class, but you're not in class, so I just wanted to correct that and move on. Well, now the error term, this Taylor's theorem on the remainder, and so if we take the absolute values, the error will give us upper bounds on the error. We'll see that, again, believing our calculator, we'll see that the upper bounds that we get aren't exactly the error. The error is actually less than that. But okay, at least we get some upper bound on the error. So let's see what Taylor's theorem tells us about how accurate this is to the actual value of that. So so a is 0 for us, and right now we're wondering, so a is 0, and we're wondering what the remainder is, or actually its absolute value. I'm going to suppress the of a when we look at x is 0.1. Okay, so we're still dealing with f of x as e to the x. Taylor's theorem says that there's some c between x and a. Well, that's between 0 and 0.1, so that this remainder is given by this. But all the derivatives of e to the x are e to the x. So this is just the exponential function evaluated at c, so that's e to the c. So Taylor's theorem tells us that there is a c between 0 and 0.1, so that this remainder equals e to the c over, n is 1, so you get 2 factorial, that's 2, times x minus a is 0, x is 0.1 to the 2. So this, this is for some c, such that 0 is less than c is less than 0.1. Well, how does that help? We don't know what c is. So how does this help us decide what the error is? Okay, well, first of all, we only care about the absolute value of this. Well, everything over here is positive. E to the anything is positive. So this is also the error. That doesn't always happen or even usually happen, but this is the error. But how do we get any grip on this at all? Well, e to the x is an increasing function. We know that from its derivative. Its derivative is e to the x, which is always positive, which means if c is between 0 and 0.1, then certainly e to the c is less than e to the 0.1. So we know that this, if we want to get rid of the reference to c, we have no way of finding c. It's just a theoretical result that, oh, there is some c. But what you try to do is eliminate the reference to c. Yes, this is true for some c between 0 and 0.1, but in fact, since raising e to powers is an increasing function, we know this is less than e to the 0.1 over 2 times 0.1 squared. But now you should be slightly bothered. How do we know what e to the 0.1 is? Well, you could ask your calculator. But part of the point of this is to know that your calculator is getting things right, so somehow it doesn't seem fair to ask your calculator what this is. So we'd like to say that this is less than something that we can do by hand so that we don't have to believe the calculator answers for the values of e. You don't have to do this. You could, by some other method, have some bound on e to the 0.1 or believe your calculator and then see what kind of bound you get. But what I'm going to say is that, well, e is less than 3. And this is to the 1/10th power. And e to the 1/10th will be less than 3 to the 1/10th power. Well, what's 3 to the 1/10th power? Well, who knows? But I'll tell you this, it's less than 2. It's certainly less than 2. It's actually very close to 1, but why is it less than 2? Because 3 is less than 2 to the 10th power. It's not, 2 to the 10th is a lot bigger. So we can use this gross upper bound of it's less than 2, and now we'll have that this is less than 2 over 2 to the 0.1 squared. Well, that's great. These cancel. This is 0.01. And so what does all this tell us? We know by hand, without using a calculator, that the amount of error in the approximation of e to the 0.1, just using the first Taylor polynomial, the first order Taylor polynomial, is less than 0.01. We don't know how much less than, and we took some crude upper bounds, like we just, yeah, there's some c, and okay, e is raising e to powers is an increasing function. So we know it's less than this. That's less than 2. So this is a crude upper bound. There's no reason to expect that that's terribly close to the actual error, but at least you can say the error is less than something by hand. The actual error that we found last time, believing our calculators, was that when n is 1, what we actually found for the error was, I should have it written right here. Oh yeah. The actual value of the error is, we had 1.105170918808 for the actual value of e to the 0.1, and then if you subtract 1.1, so the actual error is more like, that just subtracts this part, was more like 0.00517. So we've got, our upper bound is like almost twice the upper bound. But so what? I mean, we did it by hand. We just want something that we can know is correct theoretically without having to rely on the calculator, because somehow the calculator has to know how accurate it is. Okay, well, how could you improve this? Well, you can take higher order Taylor polynomials, and you expect to get a better upper bound on the error. You won't know exactly the error, but you would hope that Taylor's theorem would enable you to get a much better upper bound on the error. Does it? Yes. So what happens if we come over here and change this to a 3? Well, that would still stay as e to the c, right? So you change the n to a 3. So then this would be 3. You'd get the fourth derivative of f, but it's still e to the x, evaluated at c, so we still get e to the c. N is now 3, so this is 4 factorial, that's 24. This is now 4. We can still use the same, this is 24. This is 4. This is 24. This is 4. 24. And so we get that this is less than 1/12 of 0.0001, which is less than 0.000. Well, this is less than what we should get if you divided by another 10. We could divide by 12, but if we're just trying to get ballpark, this is less than 0.00001. So yes, we know that we get accuracy to within 5 decimal places if we go higher, if we take n equals 3. And if you check the numbers that we found last time, you'll see that that's true. Okay, great. So what's another typical question? So we can plug in specific numbers and ask, okay, what does the Taylor's theorem tell us about an upper bound on the error? But what if we want to say, I'm going to use, I know that x has absolute value less than 1. So I know x is between plus and minus 1. How big does n have to be for me to know for sure that my error in approximating by the nth order Taylor polynomial is accurate to within 1,000th? So we're going to stick with f of x is e to the x, but now not fix a particular x value, but say if I know x is close enough to 0, and how close to 0? Within plus or minus 1. So our question now is, if we know the absolute value of x is less than 1, so x is somewhere between minus 1 and 1, how big does n need to be for Taylor's theorem to tell us that the nth order error term, and again we're going to center at 0, so I won't write the of a, to tell us that this is less than, we want less than 1,000th. Yeah. The question is, how big do we need to make n so that, you could record this for all times. Oh, you could write this down somewhere. Oh yeah, anytime I'm approximating e to the x and and I'm only looking at x values between plus and minus 1, I have to use maybe n is 3 or n is 4, the fourth order Taylor polynomial, to get to within 1,000th. All right, let's see what you have to do. Again, we're looking at f of x is e to the x. So that what? Well, the remainder term still looks like e to the c. So the nth plus first derivative of e to the x is e to the x, and you evaluate at c, where n plus 1 factorial times x minus a, so that's just x to the n plus 1, and this is, again, c is somewhere between 0 and x. Now, we don't, I should say, and I should have said this before, When x is a, there's no error. So when I say c is strictly between a and x, yes, right, that was just so I could say there's a c strictly between a and x. But when x is in fact equal to a, so there is no c in the open interval between them, the error is 0, because then the Taylor polynomial equals the function. So we don't have to worry about kind of, oh, do we have to really worry about where x is not equal to 0? So we're getting that the remainder term is this, where either 0 is less than c is less than 1, or minus 1 is less than c is less than 0. Okay, so we have this. We want to know the error. The error is the absolute value of this. So the absolute value of this, the error, is the absolute value of this. Well, this is already positive, this is positive, but x might be negative. So you can just write this as the absolute value of e to the c is e to the c, n plus 1 factorial. Then you get times the absolute value of x to the n plus 1. Again, we're going to use that e to the x is an increasing function, so that the biggest it ever gets between, when c is between minus 1 and 1, is e to the 1. Okay, so that's e. So we can say this is less than e to the n plus 1 factorial. We're also assuming that the absolute value of x is less than 1. The absolute value of x is less than 1. When you raise it to a power, it's still less than 1. So this is less than 1. So in fact, we know that the error is less than e raised to the n plus 1 factorial. Well, again, we don't necessarily, it depends on what you want to assume here, but I'd like to not use my calculator for the value of e, so let's just say we know e is less than 3. So what we find after all of that is that the error, the nth order Taylor error, we really assume that x was not 0, but the error when x equals a is 0, so we can say this at all. When we're referring to c over there, we were assuming x wasn't 0, but now we can just say this everywhere, or for the absolute value of x less than 1, that this error is less than 3 over n plus 1 factorial. And what we'd like to know is, okay, how big does n have to be? We want for this to be less than 0.001, 0001, less than 1,000. And then we'll know that the error is less than 1,000. So the question is, how big does n have to be to make this less than this? The bad news is that there's no good way to solve for n plus 1 algebraically. Yes, you can divide by this, and put this over there. So yes, it's true that this means that this is equivalent to, divide this, put this over there. This is equivalent to 3,000 is less than n plus 1 factorial. So this is what we want, that 3,000 is less than n plus 1 factorial. Or in other words, we need to pick n so big that n plus 1 factorial is bigger than 3,000. How do you do this? The good news, bad news, you just stick in a bunch of n's and see when it happens. It's not particularly difficult, but let me do it. So you can just look at values of factorial. So 1 factorial, let's start someplace reasonable, like 5 factorial is 5 times 24, so 5 times 4 factorial. So this is 120. 6 factorial, well, you multiply 5 factorial by 6, so you get 720. 7 factorial, it's 7 times that. 7 times 6 factorial. So 7 times this, you get 4,900, right? 7 times 7 is 49. So you get 4,900 plus 140. So you get 5,040. Well, 5,040 is bigger than 3,000, and it's the first time this happens. So we need for this to be 7 factorial, which would mean n is 6. When n is equal to 6, n plus 1 factorial is equals 7 factorial equals 5,040. So that's enough. You need n to be 6. So let me summarize what we've just said, that e to the x is approximately the 6th order Taylor polynomial, so centered at 0, so Maclaurin polynomial. It's approximately that, and we can say something about how good this approximation is. If, and this approximation, if the absolute value of x is less than 1, this approximation is accurate to within 1,000th. It might be much more accurate than that, but the abstract upper bound that we get is that it's accurate to within 0.001. So this is how you use the Lagrange Taylor's theorem. That actual expression for the remainder is called the Lagrange form of the remainder. I want to do one more example, not centered at 0, and just so you can see how you eliminate the reference to e to the c. That's always a goal when you're trying to use Taylor's theorem to approximate error. You have this expression that has the n plus first derivative of the function evaluated at this mysterious point c. Well, that doesn't give you a number, and you have the theorem doesn't tell you anything about how to find such a c. So you need to say, this thing with the c in it, or the absolute value of the remainder with the c in it, is less than or equal to something that doesn't have the c in it. So that here we use that e to the x is an increasing function, so we took the largest possible c and said, it's less than what you get there. You always need to eliminate that reference to c. So let's do another example. I want to look at another example that we looked at in the last section, but we didn't look at the error. Now, I want to take f of x is sine of x, and a is pi over 2. Okay. What can we say? I'm going to ask some questions like I asked in the last example, but first let's just ask this general question. What upper bound can we put on the nth order error term? A is pi over 2 for us, but we don't know any of those other things. Well, the theorem tells us that this equals the absolute value of the n plus first derivative of sine, evaluated at this mysterious point c that's somewhere between x and pi over 2, divided by n plus 1 factorial times x minus a, but a is pi over 2, to the n plus 1. Great. We would like to eliminate the reference to c. We'd like to say this is less than or equal to something that doesn't have the c in it, so that we actually have some bound that we can work with. Okay, how do you do that? In different problems, you do different things. In this one, you think about all the derivatives of sine. The derivatives of sine, the first derivative, cosine. The next derivative, negative sine. The next derivative, negative cosine, and then it comes back around to sine. All the derivatives of sine are plus or minus sine or cosine. So this n plus first derivative of f, regardless of what n is, this function is plus or minus sine or cosine, evaluated at some c. How do we deal with that? The absolute value of sine or cosine is always less than or equal to 1. Right? The biggest sine and cosine ever get is 1, and the smallest is minus 1. So in absolute value, the absolute value of this part is always less than or equal to 1. So you can immediately say, you can just drop out this because we know this part, its absolute value is less than or equal to 1. So we get this is less than or equal to n plus 1 factorial over x minus pi over 2 to the n plus 1. That is really nice. So what does this mean? It means if we pick an x and know how close it is to pi over 2, then we can say, and we know how big n is, or we want to calculate how big n should be to make error small, then this expression will do it for us. So let's see what that enables us to answer. So suppose x is within 0.1 of pi over 2. Then how big does n need to be for our upper bound to imply that En f at x is less than, okay, what's reasonable? Oh, let's say 1,000th again. All right. What does this line mean? Suppose that x is within 0.1 of pi over 2. That means x is within plus or minus 0.1 of pi over 2. That's exactly the statement, and you need to know that this is the same. This is exactly the statement that the absolute value of x minus pi over 2 is, and now it depends on, when you say within, do you include, like if it's exactly 0.1 away, I would say in common speech, yes, it means that. So what this line says is that this is less than or equal to 0.1. That's exactly the same statement. That the absolute value of x minus pi over 2 is less than or equal to 0.1 means, right, absolute value of the difference of two numbers is the distance between them. And we're just saying the distance between these is 0.1 or less. Well, that's what this says. All right. So what? Well, we had that for sine of x, we had that, this is a mistake. This isn't just x with nothing. This is pi over 2. Right? That was a mistake. You should have the center indicated there if it's not centered at 0. So we just found that this is less than or equal to 1 over n plus 1 factorial times, oh, there's another mistake. There's another mistake over here. I had absolute value signs around everything. And I said, oh yes, the absolute value of this is less than 1. And you take the absolute value of this and the absolute value of this. Well, n plus 1 factorial is positive. This could have been negative. I should have had absolute value signs around this as well. That very careless mistake. So, come back over here. Let's try not to make any more mistakes. What we have is that this is less than or equal to this. But we're assuming that x is within 0.1 of pi over 2. So this quantity, without the n plus 1, is less than or equal to 0.1. So this is less than or equal to 0.1 to the n plus 1 over n plus 1 factorial. But this is easy to deal with by hand. This is 10 to the minus third. All we would need is n equals 2 is certainly enough. When n is 2, so we would get, if n equals 2, well, if n is 2, you would get, you would get 0.1 cubed, but that is 1,000th, and divided by an extra 6, right? 3 factorial, so 6. So yeah, I mean, we get better accuracy than this. Certainly, if this is 1,000th already and you divide by 6, we know that this is true. When n is 2, we wouldn't know that. This would be, sorry, if n were 1, if we just use n equals 1, we would get 0.01, and then divided by 2, so we get 0.005, but we wouldn't get something better than this. So n equals 2 is enough. Now, we might not need n equals 2 for some x values, but this is what we can calculate easily as an upper bound. If n is 2, we know that there's an upper bound of actually 1,000th divided by 6. So what does this mean? Well, we looked at this Taylor polynomial centered at pi over 2 last time. Let me just write out the Taylor series so I won't stop at any particular n. What we got were the even powers with alternating signs. So what we got for this, or I would also write this without an n. You can think of it as the infinite one, or just to save on some notation, just say, oh, when I omit this superscript, it's this. What we found last time was we got all of the even powers with an alternating sign. So we had and so on. So you get all of the even powers of x minus pi over 2 divided by the corresponding factorial, but the sign alternates, plus, minus, plus, minus. This is what we got, and what we just found is that sine of x is approximately, we said we could use the second order one, is approximately 1 minus 1 over 2 factorial times x minus pi over 2 squared. And how good is that approximation? What we just said is if, so this is, we expect this to be good when x is near pi over 2 because we're centered at pi over 2. If the absolute value of x minus pi over 2 is less than 1/10, then the approximation is accurate. The approximation by this is accurate Well, we only asked for 1,000th, but what we found is accurate to within 1,000th over 6. Oops, 1,000th. So that's pretty good. I want to say one more thing about this before we stop with this section. So, okay, two more things. I want to say one more thing about this specific example, and then say a general thing. You should notice that the Taylor polynomials for sine centered at pi over 2, you get the Taylor polynomials just by chopping off this Taylor series at whatever order. Oh, there's another mistake. That should have been a 4. Just all kinds of little mistakes today. You get the appropriate Taylor polynomial by chopping off at the right order. But what this means is, for instance, the third Taylor polynomial and the second Taylor polynomial are the same, right? So, right, if you take, in this example, this is the same as this, because the third order one means you go out to the x cubed term, but it's got a 0 on it. So the third order Taylor polynomial and the second order Taylor polynomial are the same. Okay, whoopee, who cares? Well, actually, we care, because we said that E2, we found that E2 was less than, what we just showed was that E2 is less than 1,000th over 6. Great. So what I said was, how good is this approximation? Well, we know that it's accurate to within 1,000th over 6. But T2 and T3 are the same, which means E2 and E3 are the same. The error in approximating by them are the same. And you should think, so how does that give us anything good? Well, so all I'm saying is that because the cube term is missing, the Taylor polynomials of order 2 and 3 are the same, which means the error terms, when you approximate by them, are the same. Well, it means that the Lagrange form of the remainder can actually give you some better data. Why? Because it gives you a rough upper bound in terms of n, and it might be better for E3 than for E2. It seems kind of magical that just because that term's missing, we get a better error, but it's because it's there exists AC that makes this true, and it's just a rough upper bound, and it's and it can be better if you use the Taylor's theorem. So let's see how that works. What is E3? Well, E3, it's the absolute value. It's the absolute value of the nth plus first derivative, so the fourth derivative of f, which is plus or minus sine or cosine. In fact, we know which one it is this time, right? The first derivative is cosine, and the second derivative is minus sine, and the third derivative is minus cosine, and the fourth derivative is sine again. So it's sine, but that doesn't do anything for us because it's still evaluated at this mysterious c, divided by 4 factorial times x minus pi over 2 to the fourth. But if we're assuming that x minus pi over 2 has absolute value less than 0.1, we also know this has absolute value less than 1 because it's actually sine of c, but we know, in fact, that this is less than or equal to, so this is less than or equal to 1 in absolute value, this part, is less than or equal to 0.1 to the fourth and divided by 4 factorial. So, yeah, what does this tell us? It tells us that this approximation that we already thought was really good, that it was accurate to within 1,000th over 6th, is actually better than that. It actually has to be accurate to within, this is a 10,000th divided by 24. So 0.0001 divided by 24. So actually this is a stunningly accurate approximation for x close to pi over 2. You get this improved accuracy, or I shouldn't say that. It's not improved accuracy. It's our knowledge of how accurate it is improved by thinking of this as also the third order Taylor polynomial instead of just the second one. The accuracy is whatever it is, but our knowledge as to what the accuracy is improved by thinking of this as a higher order Taylor polynomial. All right, well, most of the problems about using the remainder are of the forms that we've looked at. The other thing that I want to say before we stop is that we do want to make sense of an infinite sum. Right now we have infinite Taylor series just as a formal expression that's like a polynomial that never stops. But what we'd like to know is that, in fact, kind of that there's a limiting sum there. There's some, you can view that as a function, and you'd like to know when that kind of infinite polynomial equals the function you started with. Well, it's going to be a question of if the remainder approaches 0, if as n goes to infinity. So if you make n big enough, so as you take larger and larger order Taylor polynomials, does the error in approximating by that Taylor polynomial get arbitrarily small? If so, then we're going to say that, well, that the function is the limit of the Taylor polynomials, and that'll be nice. And then we'll have this notion of what an infinite sum means. It really means the limit of all of these partial sums. So that's where we're headed. But these error approximations are actually very valuable. As I said, you can just record once and for all that if your x value is this close to a, then I need this order Taylor polynomial to know that my approximation is good to within this. That's very useful in practical applications in engineering and in physics. All right, next time we'll do new stuff.